Okay, so basically in this next segment, I want to talk a little bit about myelin and the importance of the myelin sheath. Okay, myelin basically is a fatty insulator that you find around the axons of neurons, especially in heavy abundance of the peripheral nervous system. Okay, now again, the peripheral nervous system aren't the only neurons where you find these. Okay, but, I'm just giving an example here. All right, so again, myelin is a lipoprotein. And again, it's about 80% lipid and about 20% protein. Okay? And basically, myelination begins very early in life before we're born, but doesn't finish until after we're born. Okay? It doesn't typically end until, it doesn't really significantly end until we're in our, the toddler years of life. I mean, that's when a lot of myelination has occurred. Okay? Now, basically, the myelin sheath, what it does, like I said, it's an insulator, and it allows us to send action potentials at a lot more rapid rate. Okay, meaning we can send nervous impulses a lot faster with myelinated axons than with unmyelinated axons. Okay, so for example, I gave the example of the peripheral nervous system because if I need to get an impulse from my spinal cord all the way down to my all the way down to the flexors or extensors of my leg and my foot, to pull away from a piece of glass I just stepped on. Okay, we have to send that impulse as quickly as possible. Okay, so that's the importance of myelin, is it increases the conduction velocity of action potentials. All right, now if we want to break down myelin or myelination, remember myelin is created by a cell. Remember, the cells in the central nervous system that produce and maintain myelin are called oligodendrocytes, and the cells of the peripheral nervous system are called Schwann cells that maintain myelin. Okay, and kind of a little bit of a difference between these are in the central nervous system, oligodendrocytes can myelinate many different axons at one time. So you can see an oligodendrocyte with extensions branching off to many different myelin sheaths at once. Whereas, with Schwann cells in the peripheral nervous system, it's a lot more of an individual effort here. Okay, so for example, one Schwann cell, one myelin sheath. All right. Now, and remember that there are spaces in between the myelin sheath called the nodes of Ranvier. Think of these as kind of bare, exposed areas of the axon itself. All right, bare exposed areas of the axon. Okay. Now remember, the axon is where we generate the electrical impulse from the cell body down to the synaptic terminals for the purpose of sending and releasing a neurotransmitter. Okay. Now, basically, when we develop myelin, let's go with the example of Schwann cells in the peripheral nervous system. What happens are these Schwann cells come in contact with the cell membrane of the axon that's called the axoplasm. Okay, and then what they do is they basically start to secrete a substance called sphingomyelin. This is the lipoprotein aspect that we're talking about. This is kind of the fatty / protein insulator that starts to wrap around cover the axoplasm. Okay, and then what the Schwann cells do is they just continue to form many layers and then just wrap around and around and around and around the axon. Okay, and then remember, these are living cells, and they just use the nucleus to like any other nucleus to maintain the activity of the cell. For this, to maintain the integrity of the myelin sheath. Okay, so like I said, it takes a little while for this to happen. Okay, this doesn't happen all at once before we're born. After we're born, this myelination does continue to develop, and that's why. One of the big reasons why you see coordination changes take place as we grow in life, as we go from just kind of laying there, wriggling around, waving our arms around, to being able to roll over, being able to hold our head up, okay, being able to crawl, hold ourselves up, stand up, and then eventually walk around. A big part of that is because you're seeing the nervous system, you're seeing what happens as the nervous system myelinates itself, and we're able to send action potentials at higher velocities, and we can, regulate things like muscle tension and, plan out motor movements better than we could. Okay. And then the opposite of this, what happens if we have a disease like multiple sclerosis? Okay, what's going to happen? Remember, this is when the myelin sheath is destroyed. We call it demyelinating disease. Okay, and as that gets destroyed, that's going to affect the conduction velocity of these nerves, and as a result, these nerves they should be sending action potentials at high rates, it's gonna slow down a lot, which is gonna affect the coordination and regulation of that muscle, or whichever nerves are being demyelinated. Okay. Now, bear in mind this lipoprotein is an insulator, okay? And the beauty of this is that when we generate an action potential, when we need to send an electrical impulse down the axon, what's nice about this is we only need to depolarize, the node of Ranvier. When I say depolarize, in general, what I'm saying is opening sodium gates, closing them, opening potassium gates, and closing them, so we can have movement of ions across the cell membrane. Okay, and that's going to change the electrical charge, the resting membrane potential. Okay, and as a result, that's how we generate an electrical signal down the nerve, by moving sodium, potassium in and out of the cell. Okay, so as a result, with an unmyelinated axon, you have to depolarize every last little bit of surface area of that axon. Okay, whereas with a myelinated axon, you only really have to depolarize the nodes of Ranvier. Okay, so a node of Ranvier, so the axon hillock, remember, is where the action potential begins. That impulse travels down the axon, and this fatty sheath will insulate the electrical message, so it can travel underneath. And then once we get to this exposed part, then we'll open up some more sodium potassium gates, and then we'll just continue to propagate that electrical message down the axon. Okay, so people like to say that it doesn't truly do this, but it looks like the action potential jumps from node to node to node instead of traveling along every last little square inch of the of the axon itself. Okay, so myelin, like I said, affects conduction velocity. It makes nerves send impulses much more quickly, up to 5,000 times faster than a small unmyelinated nerve. Okay, another thing that affects conduction velocity is just the overall size and diameter of the axon. The larger the axon, the quicker the action potentials. If you have a big axon with myelin around it, you're going to be sending electrical messages as quickly as over 300 yards per 100 yards per second, over 300 feet per second. Okay, that's the length of a football field in 1 second. That's fast. Okay, so that's myelin. Like I said, myelin, all it is just a fatty insulator that allows us to send nervous impulses or action potentials at much faster rates than an unmyelinated axon. Okay, but again, there are certain areas of the body like motor neurons, these big motor neurons that are going from the spinal cord out to our muscles or glands, where we need to send information very quickly. Okay, and that's basically what myelin is used for. It's just an insulator around the axon.